Same thing with CO2. If I do it with CO2, this is actually, let's go to the experiment. This is we do with water, this we get with CO2. So there's a lot of branches here. I need a surface area, basically, so that's helpful. And if I simulate it, this is what we have done. Simulation, we see a difference between the two. Still, we are not capturing all the elements. I'll mention why. But even in the case of water, the type of fractures we do get, breakdown pressure will depend significantly on temperature. If I break the rock, this is a granite. If I break it with at room temperature, this is what we got also for shale. But if we increase the temperature, in this case, actually, the temperature of the fluid and the temperature of the rock are the same in these experiments. At higher temperature, we get a lot more branching. And even higher temperature, we get much more branching. And some of them, the fracture does not start from the notch. And these are the simulations that I'll discuss in detail. This is if we exclude thermal stress. This is if we include thermal stress, that I will go into details. So this is really, the talk is going to be related how to simulate these conditions or this material. And the work I have done till now has been limited more to lab scale. Now I'm working on a very large scale. If I wanted to do the same approach for large scale, I have to advance some numerical techniques to be able to do that. Towards the end of my talk, I will mention what we have to do in order to be able to do it on very large scale. So my talk going to be covering partly introduction, partly motivation that I've already mentioned, how to formulate the problem. There is a key element here is surface energy. If I follow the conventional rock mechanics approach, this is neglected basically. But in this case, if I wanted to get branching without adjustment, I need to include surface energy. And I think depending what I do with the surface energy, I make a different result. So I have to use a relevant surface energy. There is also challenging on numerical approach. What type of numerical approach I'm going to use? Then I will present some results and also the steps that we are taking to be able to do larger scale simulation of the order of kilometers or what the field scale is. There's also a need to viscosify CO2 if I wanted to put prop in there, and that's maybe what of some interest. And then I have some concluding remarks. Again, for some of you are expert in the field, geysers have been there, and here is the picture from a geysers in California. Some of you are expert on the subject, but some of you who are working on the area, just like I am. It's good to get a feeling of the problem. For geothermal, depending on where we are, which part of the country or continent we are, there are some spots that the temperature is very different than other spots in the same depth. This is a map of temperature distribution at the depth of 6.5 kilometers, which is deep basically in Texas. You see that at the same depth, there could be 150 degrees centigrade temperature difference. So geothermal is these spots, basically, where the temperature is very hot, and we don't have to go very deep. Mexico is another country. There are a lot of high temperature areas, not too deep in the formation, in the subsurface, and this is a map in Mexico. Early on, I'm an outsider, basically. We're looking at things. I found that in Geyser, the famous field in Northern California, there are some spots at the depth of 2.5 kilometers. The temperature is 400 degrees. And these are not actually being used. These are dry and very hot rock. So this may be an excellent candidate for geothermal energy production, but there are a lot of material issues that have been resolved. But in terms of energy content, that's enormous, basically. And I did a simple calculation to find out if you compare oil and gas formations with geothermal formation, what is the difference energy content? In some of these hot formations, the energy content is about 20 to 30% of the oil formations. Because the size is higher, there is more geothermal energy at reasonable depth compared to oil and gas formations. And there is one field example that CO2 has been used in sequestration, fracking, and there is also propane have been used. To the best of my knowledge, that's the only example that in tight oil formations, CO2 fracking has been done. In this case, first they did it hydraulic fracturing by water. They did not gain much from fracking. The fracking was there because of clay content. Apparently, there was not much increase in well production. But after they did it CO2 fracturing, they got significant increase of rate per well. So this is one case that everything has been done the way they should do. The only thing is the molecule of the chemical they used for viscosification was extremely expensive. There are some other issues. Most probably there will not be a repeat of this experience, although successful experience. The general statement I wanted to make along these lines is that there may be a lot of geothermal energy, and some of this audience may know much more than I do. We are looking after super hot rock, which high temperature because of energy content. Fracturing by CO2 may be in many cases superior to water, depending again on the type of rock and the temperature. The reason actually CO2 may work better or may have the feature it has is mainly because of one factor, and that's the surface energy, lower surface energy. Now, just this very simple calculation show what is the energy content of geothermal formation, basically related to the capacity of the rock, in this case granite, and its capacity of water if you are going to use water, basically to extract the heat. So these are some numbers I have put here, and then come up with the idea that the heat content is significant, and I'm sure most of you may have done this simple calculation. Now, there is one point here is that if I'm going to use water for heat removal or heat extraction, the capacity of water, this is at the saturation point, increase a lot, and that's for when we are near the critical region, there is a significant increase in the heat capacity. So water in this range could be a good carrier fluid, and CO2 for other reasons also may be a good carrier. So we need temperature basically around 300 degrees centigrade to get and higher to get benefit of water to be used as a medium for heat extraction. Now, these are me to just show you a couple of experiments they have done, fracking by water and by CO2. And this is mostly granite type of rock, and we'll see what is the difference. These are related to rocks or geometries used in the experiments. You see here, in this case, if you use water, the breakdown pressure is about 12 MPa. If you use CO2, we get something 9. So it's not that big of a difference we saw before, but this depends also on temperature. In the case of water, from expansion or from compression, there's not a lot of change in temperature, but in case of CO2, there is change even in this case that they have done. These are about 40 degrees, 30 degrees centigrade. Still, CO2 is supercritical in the condition they have done. And the type of fractures from CO2, this is the type of fracture with CO2, this is with water. These are room temperature conditions. So there is a big difference, basic difference at lower temperature, at higher temperature. Both of them, we get different results, but even more so for CO2. In a modeling framework, there are two modeling frameworks. One is basically use solid mechanics principles, conservation of mass, conservation of energy. In this case, basically, you have to twist the model a lot to be able to get the fracture propagation and the shape. It's not this is not within the thermodynamic framework, basically. The second approach is the phase field, which really have phase field. Part of it is we have to include the surface energy and minimization of energy, like a lot of other problems we have. So this, we should get everything we want from it if we can do it properly. So it provides information on fracture initiation and fracture propagation. Shape and branching are readily predicted without adjusting parameters. I think it's very different from purely solid mechanic or conventional approach. So in phase field, what we do, we have a domain with a fracture. So what we do, we make it continuous. So it's not going to be abrupt change from a fracture to the matrix. There is a transition region. We can make it very small. This is called the regularization length, and we can make it as a small or even smaller than the fracture itself. So in our case, what we did, I started with a lot of molecular simulations to get the knowledge of the process. So I'm listed some of the work we did to understand fracturing, basically. Now, in terms of idea of the phase field or part of the phase field is Griffith basically theory that potential energy not only related to the work or to the aspects from the stress or strain part, but also related to surface energy. This is over the volume, this is over the surface or the line, depending 2D or 3D. We also can include kinetic energy at lab scale. In case of CO2 is important, so we can include potential energy, which includes the surface energy of the crack and then also kinetic energy. The idea here is that when you take a piece of rock and you expand it, you see, you stretch it. Basically, we are doing a lot of work. After this breaks, suppose this is fully elastic, all the bonding is the same as before. So we have put a lot of energy to the rock. We have done a lot of work. Where did all this energy go? Here, Griffith's idea is that all this work we have done, all the energy has gone to a surface which has energy base. So really, that's the essence of the argument. So because the cracked rock, the surface created as energy, so all this energy have gone there, and minimization, we can find the surface area or the shape. The framework here is Lagrangian, again, the phase field, which is the difference between kinetic and potential energy. If I have a basically pendulum too, and if I wanted to see the movement here, if I use Newtonian mechanics, is going to be difficult. If I want, I can do it, but if I have 2 or 3 pendulums, it's going to be difficult. So if I use Lagrangian formulation, then I will try to get the energy functional here. This is this basically energy parameter here is kinetic energy and potential energy. And then I can basically integrate it over time. And then once I do that, then I can also get a minimum of this energy functional with respect to the variable I have, and that is equivalent to the minimization of energy we use in different form for a lot of problems. So that's really one of the items for formulation. So here, the type of effect we have, the fluid has effect, basically stress has effect, and temperature has effect. So all of them we put in the effective stress, and then we calculate the elastic strain, which is going to be various parameters here from the tension, from the extension, from the pressure, from the thermal effect. So, and then we can put it all together in some form, which I'm going to go a little bit too fast here. These are given in different papers. So this is the parameter that we are after, and then we have to minimize that parameter with respect to various variables and get the equation that you need. So if we do that, we get the momentum balance, which is related to displacement of the rock. We get the phase field that somehow I went too quickly through. This parameter comes in. This is phase field parameter, which is going to tell us where we have the fracture or where we do have intact rock. Then we do get fluid mass balance in a different way. We have a deformable media, so it's going to be thermal effect. So this is the fluid mass balance. If I make it isothermal and I remove the stress effect, so it becomes much simpler. And I have an energy balance, basically because of a transfer. So we have 4 sets of equations. These are highly nonlinear equations. There are many different ways to solve these equations, and that may have some effect. Depending what method you use, we may get different results, and a lot of time we may get non-physical results. If you use finite element, which we don't basically, and different version of finite element we do, if we don't do it carefully, basically, we'll see at the tip of the fracture, we do get very, very large, very, very, large negative pressures, depending on what method you use. For lab scale, at least, what we have found out that initial term should be kinetic energy should be taken into account. There are fundamental differences from what we have learned from the phase field and also just the application of solid mechanics. We cannot get branching. We cannot even branching if we don't use the right parameter. There are a lot of papers in the literature. In the phase field, they don't get the branching because of very large values of parameters. In our work, because of previous experience, we use a mixed finite element. We think is a natural choice for discretization, and also for different reasons. We use it actually for the fluid expression, the mass balance. We use it for the phase field and use it for the energy. And I will tell a little bit why. We use the conventional finite element for displacement. We don't have issues with using conventional finite element for displacement of the rock. And the critical element in the phase field is the surface energy, or in a different way, it's called critical energy release rates, which account for different fluids. And that actually relates to adsorption, similar to what we do in fluid interfacial tension, which is integrated in the formulation. Now, if I wanted to look at the failure of a rock, there is a conventional approach, which is the Brazilian test. And you stretch a rock, we see what is the critical stress when the rock breaks. Here, the Griffith idea is that depending what is surrounding this rock, the rock may break differently. If I surround it with CO2, the rock will break differently than if I surround it by water. If I do it at different temperatures, I will get different effects. And these tests, we may not be able to do it with all the parameters that we are interested. So we try to do molecular simulation of this test and get some of the material properties of different rock systems. So all you can do, we have constructed, we were interested in shale. So this is kerogen part of a shale. So we have constructed kerogen, we can stretch it, we can compress it. And from this, you may be able to get Young modulus and some other parameters too. So this is basically the molecular simulation we did. We took 2 different types of media, illite and also kerogen. Kerogen is just a very flexible molecule, and what we do, basically we displace atoms about 0.5 angstrom in every step and wait for a while so that get near equilibrium and do the. Here, this type of work also gets an idea how to get the surface energy of the rock. So here, basically, if we wanted to get Young modulus is what we do. We do extension, compression, and then from the slope we can get the idea. And we get the elastic part and inelastic part too. To get the surface energy, this is what we do. Surface energy base for both fluid and solid. If we wanted to get it from certain approach, we take a system, phase one, phase two. One of them could be gas, the other one solid or liquid. What we do, we perturb it or we change the surface area, increase it. So that means compression. We expand it. Basically, that means we decrease surface area. From this difference, we are able to get the surface energy. And there's a fundamental difference between how we do get it for fluids and solids. In the case of fluids, actually, when we change the shape of a fluid, there is not much need for work. The surface area part that we need to do work on. But for solids, if you wanted to change its size, there is a lot of work, basically. And that's what makes the surface energy calculation of solids and fluids different. So this is the Helmholtz-Sprengel expression for deformable media. If I wanted to have fluid, this term becomes minus PdV. One complexity in solids compared to fluids is that here in the bulk we are dealing with not dealing with pressure and volume, which are scalars, but then we are dealing with the stress and energy. These are tensors, so it makes it more complicated to do this calculation to understand the concept for the case of the deformable solids. So the difference really here is this term. Case of fluids, much simpler. If it's a fluid, if I want to change Helmholtz-Sprengel energy at constant temperature, volume, and for a closed system, I change the surface area, and simple way I'll get it. But for the case of solids, if I wanted to get the surface energy of a fluid solid system, I have extra term due to the stress and the work I have to do to change the shape of the fluid. So those are the parts. It's extra. We can go through the process. We have done it. Now, suppose in the case of I wanted to break kerogen. If I have it with CO2, have it with water, in contact water, the surface energy related, you see they are different by a factor of 4. The critical stress, where I can break it, you see, with here in this simple system that I have, the stress, the critical stress for water is twice of CO2. I can break kerogen much easier than with water. So there's no chemical reaction basically here. That comes from the absorption part. And then we can see the difference with vacuum, the effect of temperature. So these are the parameters that we have looked at. For the discretization, I will show the example for flow, how we do it. In conventional finite difference method, basically, we divide the domain into different grids. We calculate the pressure for this grid, the other one, and the flow is driven by this pressure gradient. In mixed finite element, what we calculate, not only we calculate the pressure of the, say, average pressure of the grids, but also we calculate pressure at the interfaces. This is called trace of pressures or pressure traces. We also impose the condition, whatever comes here, they leaves here. So we don't have, if I don't impose this, I will have material balance error or energy balance error. With this, I don't have that. So and then I can also, the advantage here, over here is that I can have any type of shape base. It doesn't have to be orthogonal grids or doesn't have to be any kind of shape I can describe. So there's a lot of advantages in mixed finite element over some other types of finite elements. So here, basically in this approach, if I have a triangular element, from every flux from every phase is related to pressure at other elements. This is pressure at other phases here, and also a a shape function and then viscosity. So basically, I take into account pressure traces. So the flux is more accurate basically here. And from the continuity that imposed at the interface, so I don't have material balance of it. I can have any shape. So I can have this shape with different lengths. So this gives me freedom for many respects. And there are some details how I do that. There's a weighting function. There is permeability tensor, which I can do it for other approaches, and I can also have the viscosity of the fluid. So with this, I can now start simulating to see what is the difference between CO2 and water. Can I simulate it without much adjustment? So this is what we took from early on, which I showed, experiment that has been done with water and CO2, the same type of shale. And let's see what we do, get the same injection rate. So this is for the case of water. This is for the case of CO2. What we don't get, the work we did at then, this was 2021, after the pressure behavior after fracture, we were not able to predict it properly. That's important when we have natural fractures, we wanted to simulate it. So we should allow proper deformation of the fracture with pressure. So to do that, and that's something we have not even published now, we are doing it. For the case of the fracture propagation and fracture shape, we get some trends, but still we are not getting exactly what we do. There are some recent work, they do some adjustment, they get some aspect of this, but we don't get it. All this work we have done actually is limited to 2D. Because in our work, we don't know where the fracture are going to go. We have to find grid everywhere. So actually, we cannot do, or when we did the work, we could not do it in 3D or larger problem. This is limited to only lab scale because the grids are very small and we need a lot of grids of, say, 0.5 millimeter for the whole system so that the fracture could go everywhere it is. So there's a limitation, and then I will mention shortly how we are solving the problem. In the case of the water fracking only here at different temperatures, it seems we get some trend. If the temperature is the same fluid and the rock have the same fluid, we get less fracture intensity than if the thermal stress is taken into account. With thermal stress, we do get more fracture basic intensity, and the temperature itself lowers the fracking pressure and also gives us much more fracture. And the fractures, even for the case of water, they are not, vertical or horizontal. There is basically branching in that case too. And this is unpublished work. We have looked at a couple of different types of granite. This is related to geothermal. These experiments are different types of granite rock. This rock is very unusual, has a very high porosity. The other one porosity is low. These are all of them are tight, and water is used in fracking these. CO2 also used, and we'll see the difference in this slide. So this is actually a key slide, just from the observation, what is happening. If we inject CO2, all of them at 250 degrees. If we inject CO2, basically, these are the type of fractures we do get, and the pressures we do get. If it is 55 megapascal, this is 41, this type of fractures we do get. In this case, because the porosity is very high, the test is stopped too early, but we do get a lot of fractures here. In the case of water, is nearly incompressible, but it still has some low compressibility. We do get higher breakdown pressure, not to the extent we got it before, 55 versus 67. Less fracture intensity for water. For this rock, 41 versus 69. Here there is basically not a lot of branching. Here we get fracture, and some of these fractures start from what is some microfractures in the rock itself, and this is for CO2 and the last one 3640. So there is branching a lot, which the test has not continued. So there is basic difference in the case of volcanic rock in terms of breakdown pressure and fracture intensity. And this is some rough simulations we are doing. These are all 2D. We should do 3D. We see that if we assume that there are some initial fractures in the rock, this is what we do get. If we assume that there are no initial fractures, this is what we do get. So we do get more branching here, the fracture starts here, and the breakdown pressure is lower if we assume initial fractures. If we don't assume it is higher, and these fractures may not be at the wellbore is spread here. And these are again some approximation we have done. And there are two items that I wanted to discuss and briefly before concluding my talk. One is that the approach we are using is not cannot be done for larger 2D scale and for 3D. So we have to introduce something called dynamic adaptive gridding. We have to do gridding, small grids, only close to the fractures. So what we do, suppose I have this element, so we have to basically refine it. And I think here I can refine it more. As a result, we have a small grids where we need it. Therefore, we can do the computation. It's going to be much faster. So this is, and also we have to allow for the compressibility of the fluid. CO2 is very compressible. Even water, there are compressive considerations. So that's what we have done. We have done the work, completed the work on a related problem. And I thought we are incorporating in fracking part. I just show you the example for a related problem. When CO2, suppose I'm doing CO2 sequestration, CO2 dissolves in water, water becomes heavier. As a result, I have what we call gravity figures. Exactly the same problem in fracking. So if I wanted to capture it, I have to do it. If I do it by dynamic adaptive gridding, the process is much faster. So let's see what we do get here, just to show you. So this is dynamic adaptive, in which reduces the number of grids enormously, basically, and completion time increases. In these cases, even in this small system, it increases about 10 times, and the number of grids is much less. I can do it any level of gridding. If you do it 2 levels, these are the number of uniform grid I need for this geometry I showed. If I do it adaptively, we get less. If I do 3 levels of gridding, if I do uniform gridding, I need 60,000. If I do adaptively, it's much less. If I do it 4 levels of gridding, I need 240,000. These are all 2D. If I do it here, I need much less. And I gained also computational speed here. So we have to do it dynamic adaptive gridding in order to be it. So that's one part that we are doing now. The other part is that for propellant placement, which is a key element, and hopefully or most probably I'll get some common suggestion. We have to viscosify CO2. When we viscosify CO2, we don't change other properties, or that's what we don't want to do. We just wanted to change the viscosity. So in order to have a molecule to have the optimum features, it has to have solubility in CO2, of course. It has to get to the viscosification we need. We need, say, 20 times increased viscosity of CO2. 30 times, we should be able to do that. The molecule is ideal not to be adsorbed, although in this application, absorption is not the critical issue. In general, we don't want to absorption. We don't want to molecule to lose it to water if there is water there. And we want to have high partition if there is oil basically there. We don't want really the effect of temperature on the molecule. there is effect of temperature a lot. So we wanted to minimize that. And the molecule we wanted not to aggregate for many reasons. And then we wanted to use a molecule which is environmental friendly. So in these cases, we don't have these molecules. We have to go basically engineer these molecules. Because there is a lot of need for CO2 viscosification, we have been working on it for 4 or 5 years, basically. And we have had some success. The molecules that they have been used to viscosify CO2 are in these 3 broad categories. One, very little work has been done on this type of molecules with branches. There's a lot of work on fluorinated molecules. This is the molecule which was used in the field test, basically. And there are other types of molecules which are interested. So we have taken this type of molecule because it's many desirable features and focused on. And the problem is that the molecule which is in the literature, which has basically 6 branches, is not that effective. You need 5% to get, say, 2.5 times increased viscosity. We need something much lower concentration, much more. So this is the base molecule we have taken, and then synthesized lubrizol has been jointly with us. So we can change this length. Also, with the number of repeat units, we change this length, and we see that that's a direction to go. So the relative viscosity we do get now, which is useful for a lot of other applications now, we can get it at 1%, we can get it about 3.5 times. At 1.8%, we get 6.5. For this application, we need, from the colleagues I've talked to in fracking, they tell me that we need at least 20. So it seems that there is a promise here, but it still has to be worked out. So I wanted to now draw your some conclusions. I'll try to be on time, 45 minutes. So to me, what we have found that surface energy is a key element, has a well-defined, basically, trend, and depending what we put in our simulator, we get different results. But once we do the calculations, we see that the value we get from one type of rock, we also can be give us knowledge for another type of rock. And for if the rock stays the same, we see we can use this value and we get the right predictions. Again, CO2 has lower breakdown pressure for most of the rocks that we have looked at it. Experimental also for simulation. CO2 could be also thought of efficient heat carrier fluid because of low viscosity, basically. We have basically seen that mixed finite element may be a good choice for discretization, and we have some merits basically over alternative. There are many in the literature. But the main part is that what we have that is in our work is limited to 3D. If I wanted to get all the features, and that's what we are working on to get it to work beyond the small lab scale and to go field test. I think result we have in the paper, which is reviewed in the dynamic adaptive greening, will give us 3 to 4 orders of magnitude increasing computation speed in 3D. So, and the last slide is to ExxonMobil, who funded a major project to that rise and CO2 fracking, and members of our research program also help so that we can do the work. And this is what I wanted to share with this knowledgeable audience, and look forward to your comments and suggestions. John, I'm done.
Fantastic. I mean, I really appreciate something that includes lab results and simulations in the same package.
Right. We have to do both, basically.
There are some questions.
Sure.
So Professor Bozant, he is wondering if the phase field model, well, he's suggesting the phase field model uses linear elastic fracture mechanics, and by virtue of that, it misses the enormous effect of crack parallel stress on the fracture energy. And I guess he's seen this on some gap tests that he has done.
I think there are different issues that they have brought, or there is already in the literature, the comment here, and other issues. It seems that some of these issues, there is way around or has been a way around. To me, the real testing, as you pointed out, is that take the experiments and try to see, after looking at from these aspects, either to modify the phase field, and we have actually working on that, or to see at the end if you can simulate the lab experiment. But there are different gaps and different issues with also the phase field. But to the best of our knowledge of what we have seen, that this issue could be addressed, and some of them actually is addressed. And in parallel work, what we have started to do is that some of them, we are looking at it from some molecular perspective too, to see if some of them could be addressed. But I think that's a valid question, and no theory or no model is perfect. It's an approximation. And I would be happy to engage a more discussion, more in-depth discussion on the topic.
I'm going to let you guys have that discussion one-on-one.
Right.
I think, and then the next question is Dharmendra Kumar appreciated the presentation, and he's asking if maybe you could just sort of recap what the major issues that need to be considered in CO2 fracturing simulations. I think you've talked about most of them, but maybe could you just recap?
Yes.
So basically, there are two issues. One is lab scale, the other one field scale. I think we are interested in field scale because lab scale, there's all kinds of scale related issue. To me, to go to larger scale, the first part is that we have to change the simulation and what I mentioned about dynamic adaptability for compressible flow. To the best of my knowledge, and this paper we have in review, we have used it for compressible fluids, and we see enormous gains based. So the first item is efficient dynamic adaptability to go to larger scale. One concern I have is that sometimes some of the work we see in the lab, we see a lot of branching. We may not have that much branching in larger scale. So that's the need to go to there. So I would say dynamic adaptive grading is one issue, or one major issue. For practical use of CO2, also the issue of viscosification we need to resolve. We need properties. Although there are differences in the surface between CO2 and water that I did not even touch here.
Yeah, very good. And so Yoshioka has a couple of questions, and they mainly relate to strain energy release rate as I see it here. And so he's interested in slides 36 and 37, where you're calculating G sub C. Do you calculate the strain energy release rate by breaking the atomic bond between the solid with fluid saturation? The slides seem to suggest that it's computed by the areal change due to deformation.
Yeah, this is actually the way, this is the calculation is that it's not even, we don't need that even to get to the point of breaking, or there's not bond related. It's not breaking the bonds actually at all. All you do, you wanted to see how much work you have to do to extend a surface. How much energy you have to spend to extend surface. This is really what it is. So you wanted to see what is the change in Helmholtz free energy with respect to the change in surface area, because we can relate to some other theory how to get the energy part, which I'm not discussing here. All we are doing, we stretch a fluid, a solid, the surface in contact with the fluid by a small amount of the area. the change in Helmholtz free energy with the area. And then in the case of fluids is a straightforward. In the case of solid has more complexity in it. So it's not, this is not related to the, this is not related even to breakage in the way we do the calculation here. Because the whole idea here is that when we create a surface, the surface has energy. And so we wanted to calculate that surface energy. So even if you have deformation, we can get the surface energy for it. But the reason we are interested here is that we don't have a surface area initially when the rock is not fractured. We wanted to see what is that surface energy is so that we extend or put this solid under tension to the point it breaks and create a surface area. Is just to change Helmholtz free energy with surface area. And from some other theories, we can relate it to the work that we do spend on the south.
Okay, very good.
And we have actually 3 papers on the subject. I've cited one of them. All of them, the co-author is Wu.
Okay, so that's a good lead. Search for papers by Wu. So Yoshioka has another question, and that is for the water fracturing examples with different temperatures, 200C, 350C, 450C, that we're simulating the Watanabe 2017 experiment. Did the strain energy release rate dependency on the temperature change the fracture pattern?
It did, actually. It did. You know, basically what we see here, you see here in this, we have published this paper in 2023. Here we assume that the temperature of the fluid, which is water here, and the solid are the same. This is the type of fractures we do get. If we do, also there are lab experiments that I'm not showing here. If we allow for the thermal stress, you see we do get more fracturing, basically. And I think for obvious reasons, basically. So here, there is a difference between thermal stress, which is related also to the temperature gradient that we do have. We get more fracturing if we allow for the non-uniformity or gradient of the temperature in the system. This is at higher temperature. At higher temperature, it's easier to break the rock, basically. But we have the thermal stress effect, which I related to the temperature difference between we get more fracturing or branching or extensively more fractures.
That's quite clear.
Don, this is Ali Danishi. Let me just ask a question here from Abbas.
Salam alaikum, how are you?
I'm fine, thank you. Looking at your experiments here, what is more critical? What has got a bigger influence, rock heterogeneity or temperature, whether it's isothermal or not?
I think, again, these rocks apparently, from what we see here, and we don't see in the trend of the experiment the way they have some micro cracks, so it affects the pressure. But the critical parameter here, and these are small samples, try to make them homogeneous, although, you know, these rocks are, so the temperature has the biggest effect. You see the difference, the same rock, this nearly the same. They're not the same sample, but they are trying to make, you see the difference between temperature. So this is a huge effect.
Thank you.
Colin Sayers is interested in what Professor Bazant's gap tests are. I'm suggesting that Professor Bazant can send me a publication, or he can send it to Colin directly, so that we can handle that. Would Colin, is that acceptable?
Sure, that would be great.
Okay, very good.
I think one thing I should mention that I have not gone here to the phase field, some of the details. There are different ways also to implement, to look at the phase field. I've just tried to look at some other aspects of the problem, just to give different flavors to different items. But the phase field itself needs, there's a lot of details on the phase field. There are certain approximations, there are certain limitations also.
Then we're gonna let Gong have the final question, and Gong has pointed out that there are some other publications in the literature that are showing CO2 experimental data, in particular stuff by Derek Ellsworth at
Yeah, I think right. I should say that there are also two sets of experiments that show that compared CO2 fracturing with water, they report higher breakdown pressure with water. But those experiments, there are some boundary effects that we have addressed actually in 2023 paper. That those are just artifact of the way the experiments were done.
Okay,
To me, if you look at I relate surface energy to absorption, which is the case of fluids actually, is always the case. So I see CO2 as higher for this type of rocks that we have looked at it. CO2 has higher absorption, very fast absorption, is related to absorption than water. And therefore, there may be a simple reason. Bulk of the experiments in the literature and some of the experiments we have access to, non-published material we have not been published, all indicates CO2 breakdown pressure is lower than water. There are two published reports that indicate the opposite. We have indicated actually in this paper that those were due to the boundary effects, the way the setup was, and that's at least my understanding.
well,
Thanks,
it's outstanding, and
John,
it was good.
quick
Yes.
thanks, Abbas. But Derek is in the audience. Why not let Derek?
Oh,
Okay, sure.
you,
I'm sorry, Derek, I put you on spot, but are you able to unmute yourself?
I'm still on there. Well, we have experiments, and our working hypothesis was with the CO2 fracturing, the reason for the lower breakdown pressures were that you could actually get fluids directly into the tip of the crack because of surface tension arguments based on supercritical fluid.
I think I will reject it right away with all the respect. We don't have actually, we are using supercritical surface tension. You need to have two phases. There is no meaning to surface tension. I have seen that argument. There is no meaning to that actually, unfortunately.
Fine. Well, you can look at the correlations between breakdown pressures directly and surface tensions of CO2 and water, and the laboratory results, the breakdown pressures correlate. So maybe look at try and get this paper in.
No, I think Drake, here we have only CO2 and we superheat, so there is no surface tension, fluid surface tension involved here. I saw that actually, that I don't want to go to detail. There is no fluid surface tension. I think there is also argument of the threshold capillary pressure. There's no actually, I have to have two phases in order to have that. I don't have two phases here. I have supercritical only. So that argument is irrelevant.
Yeah, well, actually in our experiments, I guess there was nitrogen, air, and CO2. So
But then they're the same thing. There is no, it will not make it two-phase. CO2 and air are soluble in each other.
Right.
So I think that argument is a big argument.
Okay. Well,
I'm going to let you two gentlemen agree to disagree on that one. And maybe continue that discussion offline.
Sure.
Anyways, fantastic presentation. I personally enjoyed it immensely, and I believe that the audience did as well. So Abbas, thank you so much.
So thanks very much for the arrangement. I enjoyed the questions, and like always, we learn from each other.
You betcha, as Gong would say. Anyways, thank you so much. We'll see everyone in a couple of weeks.
Bye-bye.